Very good morning, everybody. Can you hear me?
Yes, good morning.
How are we doing?
Great.
So today is review day. The midterm is next week, and I have posted. Let me just show you guys. I'm going to show you if I can find it. How do I get this thing? Going here, and we go under. Modules. So there's an updated syllabus, so you can see what sections we've been through, and then there is there's a set of practice problems here, and these are some old exam problems that I've been using in the past. We've done a few of them in class over the first part of the course, and today I was planning on going through. We'll see how many we can go through, but if some of you want to ask questions about a specific topic, or you want me to do a specific problem of these, you can just let me know and we'll do that. And then next week we are having a midterm, and you can see over here under announcements there's a schedule. So there are time slots available on Monday and on Tuesday. Most of you have filled in, but there's like a handful of students that has not replied yet. I sent out email reminders this morning, and so we'll do that on Monday and Tuesday. So you will need to be able to write during these exams, and there are a couple of ways of doing it. Most of you guys will have a phone, and you can actually use the phone for a document camera, just like the one that I'm using here. And I put a link here that shows how you can convert your phone into a document camera if you so desire. If you don't have a phone, or if you don't want to use your phone for this, there's a Zoom whiteboard built in. We can use that too, but let me just show you how the Zoom whiteboard, if you haven't seen the Zoom whiteboard. So just trying to find it. Here it is. So this here is a Zoom whiteboard, and you can write here. This is possible, but as you can see, it's tedious, and it works, but it's not great. It's not nearly as easy to write as when you have a piece of paper. So those are the options, and of course, if you have a tablet, you can also share the tablet screen, and you can write directly on it. And any questions on these things? So the way the midterm is going to work is that there are 20 minutes, and I will pick one of the homeworks that you guys have been doing and ask you to talk about one of the problems in one of the homeworks, and then you'll go through it. You will be interrupted as you go through it. I'll ask for clarification. I'll ask, why is this true? Why is that true? I'm not looking for like you guys just telling me what my solution says. This is not what I'm looking for. I would like to see you guys go through a problem and tell me what goes into the various steps. And so I will ask about that as we go along. And then depending on how that part goes, this will typically be like the first 10 minutes. Then the second part, the last 10 minutes, there'll then be some questions to clarify either what the first problem was about, or there'll be some questions that are either easy or harder than what you went through. And this will typically take 20 minutes. Then I'll try to tell you how I saw your exam at the end, and then you'll get an email after I have seen all the exams, outlining what kind of a grade you'll get and where you sit, where your performance was compared to all the other students that I've seen. Are there any questions?
I have a quick question.
Yep.
So I'm looking through the midterm practice, and it seems like most of the questions are related to like the more math homework questions. So is that going to be true also for the midterm?
Yes.
Okay.
We put in, so last year there were, and also in the years before last year, so in the previous years, there had been a relatively large component about change of measure, radon-nickel derivatives. And if you look careful, let me see if I have the book around. We just show you. So if you take a look here, this is our main textbook, right? So if you look in here, like we have not talked about these two sections here. The first part of chapter 3, the change of measure and these radon-nickel derivatives. And this used to be a large part of the first half of the course, and this was now taken out, and it was replaced by this background material in Hall. Like, so how do you compute interest rates? How do you look at swap rates and convert them into risk-free interest rates, and so on. Those problems are a bit more computational in the sense that you'll typically involve, or they almost always involve using a spreadsheet or some sort of computer software to answer the questions. And your midterm is not going to do that. Your midterm this is going to be more about computer conditional expectation, like solving one of these problems we're going to be doing now. I'm not going to be asking you to use Mathematica or MATLAB or a spreadsheet to solve one of these questions. No other questions?
I have one more quick question. Will topics on the homework assignment due on Friday be on the exam?
Yeah, I will post the solutions over the weekend.
Okay.
Professor, I have a quick question. Where is the link about the exam? Is the same as the lecture? Zoom link. Because I'm Monday, so I'm wondering where is the link for the Mondays?
I haven't gotten it set up yet, so
Okay.
I will. Yeah, I need to do that. So I will post these links. I'll post these links together with the schedule. So there'll be like Zoom links and probably at the top. And the way that it's going to work is there'll be a waiting room, and so we'll only have one student at a time. You need to bring your ID. So either if you have a Rutgers ID, or if you have a passport or a driver's license, you need to have some sort of ID, and then you need to turn your camera on so I can see that it's you. But I need to post these Zoom links, yeah.
Okay, thank you, Professor.
Yeah. Write it down so I don't forget. Yeah. Anything else, or should we get started? Righty, are there any wishes for what we should start with?
Can you review the the homework question related to the credit default swaps?
Yes, I can do that. I can do that. This was yeah, I can do that. Would it be okay if we do that towards the end? Because this part is this is less relevant for next week. I had not planned on asking anybody about credit default swaps. So I'm happy to do it.
Yeah, that's cool.
I would like to get some of the material that is more relevant cleared out first, so we're sure we have enough time to do that, and then I'm happy to walk you through the solution to the credit default swap. And if we run out of time, we can do it during the office hours too. This is I'm happy to do it. I would just rather make sure that we get through some of the issues that that could come up next week. I'm not going to ask anybody about credit default swaps. Okay, so maybe we could start with one of the first ones. So if you start with number one, so I think problem number one here, this is something that we all need to feel comfortable doing at this point. So what we have is we have a one period binomial model. You should expect the questions next week to be in multi-periods, right? So we have a one period model. It can go up and down, so it can move from 100 to 135, and it can go down to 85. And then there's an interest rate. The interest rate, I'm going to make it with a dotted line, is going to go from 100 to 115. So that's our binomial model. And we want to find the risk neutral probabilities. So remember what the condition is for the risk neutral probabilities. We want to find P tilde such that you have the martingale property under those probabilities. So we need to compute the conditional expectation of the discounted stock. So here we only have a one period model. So this is going to be S1 divided by the money market account. Condition on F0, right? That's the martingale property. But if 0 is trivial, this is just the empty set and everything. So conditional expectations, because if 0 is trivial, the conditional expectation is just the unconditional one. So we need to find P tilde such that this here is true, right? Such that this here is true. So what we do is we plug in. So on the right-hand side, you will have your 100. And on the left-hand side, well, I'll have 1 over, what was the interest? It was 15%. So this will be 1.15. And then we have S1 times the probability under the tilde measure. So we have a P tilde here. And then we have the up. What is S1 in the up state? This is 135. And then it's 1 minus P tilde times 85. That's the equation. That's the equation that that will give you P tilde. Right? So you solve. You solve for P tilde, and you will get, if I've done it correctly, something like 0.6. Okay, are we good on that? The next question says you should value a call. So you should consider a call with strike 95. So a call, let's remember what a call payoff looks like. A call is something that has, well, it's a call on the stock. So it's S1 minus K positive part. So the calls payoff out here, the calls payoff is going to be what? We have the two legs. It's written on the stock and have two legs. So we have S1, that was 135 in the up part. Minus the 95. Positive part, right? So we want to end up with a 40. And then the bottom one is we go from 100 to 85. Okay, so then it'll be 85 down here, minus 95. Positive part, this is going to give us minus 10. This will give me a 0. But our job is to figure out what to put out here. So what can we do is what we should do is we should set up the replicating portfolio. So we don't need to construct. We need to construct delta naught and delta such that this, the first part here, this is the number of bank units. Like in this one here, this is the number of shares. Shares of stock. Such that what? Well, such that when we hold these two positions, we add them up, we're going to get exactly 40 and 0. Right? So what will it be? You want to have S1 minus K on the right-hand side, and then on the left-hand side, you want to have delta 0. What is the value of these units at time 1? You have to multiply by 1 plus R. And then the other one, you have to multiply on to S1. And here we have two equations because we have two possibilities for S1. Like this one here, there's no randomness. Here there's randomness in this one, and here there's randomness in this one. So we break it up into two. Break it up into two. We have delta 0 times 1.15, and then you have delta times S1. We need to look at what is S1 in the upstate. Well, it's 135. And then we match it on the right hand side. What was the payoff in the upstate? That was my 40. Get a 40 here on the right hand side. And then the other one. Stock was 85 in the downstate. And the call option was 0. Right, so we have two equations and two unknowns. We go ahead and solve. And then you'll have that the question mark, right there, payoff was 40 and 0. That value you have out here, this will now be the number of shares of the bank account times the 1 plus delta times the 100. And if you do that, I get a number like 2,400 divided by 115. So if you're thinking about what should go into your exam on Monday and Tuesday, what I'm looking for is to see you guys set up these equations here. I'm not particularly interested in whether or not you can solve these two equations correctly. You can just, as we have done in class, you can use a computer program to do it, or if you have a calculator, or you can solve it by hand. What I'm interested in is seeing how you get these two equations set up. Any questions on what I've been doing here on these two pieces of paper? We good? So these ones here, the replicating. These are the replicating equations. All righty. Any questions? Okay, then try the next one. So next one we have a multivariate setting. Now we have a multivariate binomial model. So we have our coin flips as usual. These are IID, the IID with the probability that you get U. This is equal to P, and the probability that you get D, this is 1 minus P. And so now we create the stock. The stock list started out at 1, so we define the stock recursively. So we define it by the first point, and then you define it by some n plus 1. How is it given in terms of n? Well, the way that it works in these binomial models is this is our recipe. So the question says, find alpha 1 up to alpha n, alpha capital N, same n as the one up there, such that, so also want to have alpha 0, this is just set to be 1, such that this one satisfy so find these guys with alpha 0 being that, such that alpha n Sn squared, index from 1 to capital N, is a martingale. Okay, so such a question, well, we need, what this question is testing is whether or not, like, do we know what the definition is of a martingale? And these ones here are constants. Sn is the random variable, and it's given recursively in terms of this formula where we use these coin flips up here. Yeah, so the martingale property, what is the martingale property? Well, the thing that we're hunting is you want to compute expectations. So we're under the measure P here. So you want to compute expectations of alpha n plus 1 Sn plus 1 squared given the first coin flips. So psi 1 up to psi n. We want to prove that this thing here, this is the martingale property, that we want to write this here as alpha n Sn squared. So this is what we need. We need these alphas up here to make this true. To make this true. Okay, so that was the martingale condition. So we have an equation we need to hold. So let's work out what the left-hand side is. And the way to work out what the left-hand side is familiar, because here we have constants, so they can travel outside. So I can put alpha n plus 1 out here. Then what I'm stuck with is the expectation of Sn plus 1 squared. And there I'll go up and I will use the definition of Sn plus 1. So we put a square up there, and then we put the psi n plus 1 a square there, and then condition. That's what we have here. Okay, so now comes the time to use some of the properties that we have talked about in class. That we have a product here. And the first part, this is the stock price, say, at time n squared. So if I know the first n coin flips, well, this thing here is going to be measurable with respect to first n coin flips. So he can go outside the conditional expectation. Okay, so we move this guy outside. And then we calculate what is remaining in there. Okay, so what remains in there is the n plus 1 coin flip. And here you have independence of the previous ones. So the conditional expectation is really just the unconditional one, right? So here there were two things that were used. This one here uses the first one, namely that Sn squared is measurable with respect to the first n coin flips. And the second thing that it uses is that psi n plus 1 is independent of the first coin flips. So you use these two properties. The first one was used to pull the Sn squared outside the conditional expectation, and the second one was used to replace the conditional expectation by an unconditional expectation. And this is a calculation that we have done many times, and I would fully expect that sometime next week, most of you will have to use this. And so when you calculate these conditional expectations, you need to be able to tell me which property is it that you're using for that particular step. It won't work just to write this thing down as that one. Then I'll ask you, it's like, how could you do that? And then I would like to see these properties being listed. Okay. Are there questions on this step here? This is a step that is quite important. So the last part here is what remains to be done is to work out what this expectation is. Okay, so let's just work out what that one is. This is alpha n plus 1, and then you have your Sn squared, and then the conditional expectation. This is p times the value that it has in the opposite, so that is a u squared. Remember to put the square on the u, not on the p, and then 1 minus p times d squared. And so we look at what it is we want it to be equal to, and we walk all the way through here. And so we need alpha n. We need alpha n to be alpha n plus 1 times p u squared plus 1 minus p d squared. And that gives us the recursion, right? We also had that alpha 0 was 1. So we start out with alpha 0 being 1, then I can get the next one. Right, so alpha 1 is found by what? So by saying that 1 is equal to alpha 1 times p u squared plus 1 minus p d squared, right? And you solve. Yeah, put the square in the wrong place. Not good. Should go on the d. And so on. So alpha 2.
Can I ask a quick question?
Yes, of course.
So where did you get the alpha n from? Because I think we took out alpha n plus 1.
Yeah, right. This is what we need.
Oh, okay.
Right. So here is alpha n Sn squared. Right,
Oh, I
and
see.
we need that to be equal to, and then we go all the way down to here. So you this way. So I need this expression. I need this to be equal to, this is what we need. I need this to be alpha n Sn squared. Right, and so you can see this term and that term be the same. I'll have this as the same as alpha n plus 1 p u squared 1 minus p d squared. That this is again what we need. This is alpha n.
Okay, thank you.
Yep. Alpha 2 can be computed the same. You will have that. So given alpha 1, you solve alpha 1 is equal to alpha 2 times this pu squared plus 1 minus p d squared, and so on. Yep. Are there other questions or comments on this calculation here?
Professor, is that supposed to be alpha 2 equals the alpha 1, or is it if you're given the alpha 1?
So you're given alpha 1 now because we've solved this one. So now you want to solve this one. So you have alpha 1. If you plug in what alpha 1 is, it is 1 divided by pu squared plus 1 minus p d squared. So that's your alpha 1. So what is your alpha 2? Well, your alpha 2 is going to be 1 divided by pu squared plus 1 minus p d squared. But now you're going to get 2 of them, so you need a square here. So this here is going to be your alpha 2. Is that your question?
Yes, thank you.
Yeah. So you can kind of guess here. What do we think that alpha n is going to be equal to? So it's going to be equal to 1, and then pu squared plus 1 minus p d squared, right? And then instead of a 2 here, you're going to keep doing this, and you're going to get an n. So that gives you an-
I have a quick question. I see the problem, the filtration is sigma S0 to Sn. Is
Yes.
that the same to the sigma psi 1 to psi n?
This is a good question. So
Yeah.
So if I look at the sigma algebra that S1 generates, and the sigma algebra that psi1 generates, are they the same? Well, let's plug in what S1 is. This was S0 times psi1. So imagine if you observe, so say you observe that S1, well, you could take, if we are in that problem we had here, say that you observe that S1 is equal to 135. Can you tell me? Can you tell me what psi1 is? Can you tell me what this one must necessarily be if we are in this model here?
1 point is 35.
That's right. Or U if you want. So yes, these are the same. There was a question about this. I remember I had a question about this when I looked over it this morning. Maybe we should do that problem now. Yeah, so maybe we should do that problem now. So this is problem number 4. Let's try to do problem 4. So y is a random variable, not necessarily these concepts that we had over here. The question is, so the first one is is sigma squared always sigma y measurable? So then the question is, if I tell you, if you know y, do you also know y squared? What's the answer to this question?
Would be yes.
Yes. And if I do 2, the only thing I flip now is I flip the squares. Is y always sigma y squared measurable? Right. So if you know y squared, do you also know y?
No.
No.
No. Right, so could you create a little example here in the second one? Could we do Bernoulli? So my y here, what could y be? If you want to make a counter example here. If you take y to be, so y of omega, take it to be something that takes values between -1, take values -1 and 1, right? So you have a 1 here, a -1 here. It can either be heads or tails. So in that case, y squared, no matter what you have, this is always equal to 1. This is a constant. Right, so if I just, there's no information here, right? It's just a constant. So I will not be able to tell at all what values y would have had, just because I know that, because of the observer constant. And this is a constant for all values of omega. Whereas y is not, right? Y could be 1, could be -1.
So if it was y cubed, it would work.
Yes, so for y cube it would work. It would work. Yeah. So you can ask so what are conditions on f such that the sigma algebra of y is equal to the sigma algebra generated by f of y.
It would have to be 1-to-1 and onto.
So I would say, I don't like the word it has to be. So if y is 1-to-1, it's okay. And that was the one you're using, right? You're using x to the power 3, like f of x to the power 3, but f of x to the power 2, that one does not work. This one here is okay, this one here is not okay. Right, so it's sufficient to be 1-to-1, but it's not necessary. Yeah. Are there other questions on this part? Okay, so now we skipped one, so let's go back and we skipped number 3. Let's go back and do number 3. do number 3. Again, we have an end period model. Let's write down these. So again, we have an end period model. So we have our coin flips, the IID. Now we're working directly under the risk neutral measure. So we're working under, you go up and down, and here we have P tilde now, and 1 minus P tilde, which we also often call Q tilde. We have the stock price as before. You have S0, that's the starting point, and then you have Sn plus 1 is Sn times the nth plus 1th coin flip. The first question is Sn Markov? And that's something we've proven in class, and the answer is yes. How does one prove that again? Well, remember what it means to be Markov. You have to take any function f, when you plug it into Sn, when you plug Sn plus 1 in there and compute the conditional expectation. And I'm going to keep writing here the coin flips. So this is, you can either write Sn or you can write the first n coin flips. And then you compute an expectation under the tilde measure. For this to be Markov, what it means is that this conditional expectation here should just be a function of Sn. And so let's write out what we have. This is f, and then we use the definition of Sn plus 1. So this is Sn psi n plus 1 condition on the first coin flips. And now comes the time where we use, so this is where we use a result. This one here is the independence lemma. What the independence lemma says is that you take out what is measurable, right? You cannot move Sn outside the function f, right? F is not linear. Here is some arbitrary function at this point. So you replace what is measurable with a dummy, and let's call it dummy for x, and then you take expectation over the rest, right? No conditioning anymore. And then when you're done computing this thing, you replace x with Sn. Right, so here this is an unconditional expectation. This was a conditional expectation, right? So this is going to be a random variable, which is measurable with respect to all these coin flips. And let's work out what it is. So this is an expectation. I'll have the risk neutral measures. I need P tilde times f, and then it's x. P tilde, this is the up probability, plus, then it's 1 minus P tilde, f of x times, now it's d, right? And when we're done computing, we replace x with Sn, so I can do that here. This is P tilde f. P tilde f of Sn times u plus 1 minus P tilde f of Sn times d. And you can see this here really is nothing else than a function of not all the coin flips, but a function just of the stock price. And g here is exactly this function here. This is P tilde f of xu plus 1 minus P tilde f of xt. So what we proved is that give me a function f, compute the conditional expectation, and it is a function just of the current value. I don't need to keep track of all the coin flips, just the current value of this. And that makes it Markov. the questions on these calculations we did there?
I had a question of why we need the dummy variable at all if it's just being replaced.
But how would you, so you're questioning this point here. I mean, how would you calculate this expectation?
I mean, with the same way as with the dummy variable, except for I'm just not comprehending why the dummy variable is necessary.
I mean, did you want to skip those steps here and just write from here to here?
Yeah, is that possible?
I mean, this is true, right? This is you just skip a couple of equality signs. I mean, you can go from here to here in like one step and write out what G is. And this is correct, right? You just skipped a bunch of steps. So if, I mean, if you skip these steps, that doesn't make it wrong. If you skip steps on Monday and Tuesday next week, I will just ask you to fill them in. Like, what took you from this expression to say that on Monday or Tuesday, what you do is this is the calculation that you do, compute this expectation, and you write it that this is equal to G, and it has this form here. And this is correct. But then I would ask you if you could fill in a bit more detail, like how did you go from here to here? What kind of calculations, and like in general, this is not going to be this easy, but there's some particular structure that allows you to do that. And so of course what the structure is the assumption up here on these IIDs and this particular form of the S's. It is these things that allow you to go from here down to here. And so what I'm trying to do is to fill in so we can see where these steps are being used. So if you skip them in this particular problem, it will give you the right answer. But in general, I think filling in the steps is a good idea to do.
Okay, that makes sense.
It's just when you skip a bunch of steps, one can make. I think it's easier to make mistakes. I guess this is all I'm saying. Right? We had an example. Like we had an example in so just from I think it was from last time. Right, from last time we considered this max here, which was the running max of S0, S1 up to Sn. And you could try to do the same thing. You could try to say, well, let me try to compute take a function, f is arbitrary. And instead of S, I'll calculate M here. And that's the only thing that changes, right? So if you just skip the steps and then you write, well, this is equal to a function of MM. But this is not true. So by going through the steps, for example, in a case like this, that could help prevent mistakes from being made. But this is not true. What is true is you can write this here as a function of Mn, and then you also need to keep track of Sn. This is true. You guys remember these calculations we did here last time? Should we do them again?
Yes, please.
Okay. So let's try it out. So that one's not true. This one is true. Okay, so let me write it in blue here. So we'll try, we'll proceed, we'll proceed according to the same steps as over here. So the first thing we're going to do, is to write f, and then it's the max at time n plus 1. So we always want to do the same thing. You want to relate the value you have in here to values that are related to what you're conditioning on. So this is at time n plus 1. So you want to relate this thing to something that happens at time n and then at earlier times. Right? So here, Sn is at earlier time. So this is going to be measurable. So try to do the same thing here. The max at time n plus 1, this is equal to, well, the max at time n, and then the value of Sn plus 1. Right? So we will have to put in here a max of Mn and then Sn plus 1. And then we have the condition on all these coin flips. So again, we obtained a very similar structure before. Here we'll have Mn, which is good because that's measurable. And then you have Sn plus 1. That is not measurable. And Sn plus 1 is also not independent. So we need more work here. But at least we were able to really make some progress here. And so the next step, we have to break this one up. But that's now we're in good shape because we're just going to use the same thing as what we did over here. We're just going to use the same thing as what we did over there. We'll write this here as an expectation of f and then the max Mn, and then we plug in what Sn plus 1 is. This was Sn, and then this coin flip psi n plus 1. Condition, see if I can squeeze it in here. Psi 1, psi n. And now I'm in business because this one is measurable, this one here is measurable, and this one here is independent. So now I can use the independence lemma. I need two dummies now because I have an Mn and an Sn. So I can write this here as an unconditional expectation of f of max, and then I'll put in one dummy. So say a y, comma, and then another dummy, say x, and then is this psi n plus 1. And then there's no more conditioning. And then I'll have my two dummies. So when I'm done computing this expectation, I'll put y equal to Mn, and I'll put x equal to Sn. So this here was the independence lemma. So I have an unconditional expectation. I can write this here as, well, it'll be p tilde. That's the probability of going up. So I have p tilde f, and then I'll have the max y comma x, and then this is up plus 1 minus p tilde f of max y comma xd, right? And then I have the plug-in that x is Mn, no, x is Sn, it's not here, and y is Mn. And I can do that now. I can write this, let me give me some more space. So I have p tilde f of max, y was Mn, x was Sn, and then we have a u plus 1 minus p tilde, and then the same thing, f max, y was Mn, x was Snd. So now we're going to get our function here. This g is g of x comma y, right? This g here, it's this guy down here, g of x is p tilde if evaluated at max y comma xu. plus 1 minus p tilde times f max y xd. So you need 2 here. You won't be able to write it just as a function of mn. Are there any questions on doing this calculation here? So I like to fill in. You're not going to get if you fill in too many details. That's not going to make me upset. That's fine. I'll just ask you to either speed up or skip it. If you provide too few details, then I'll ask you to fill in more details. Are there any questions on slide 8 here? I think there was something about this on your homework, or maybe it's the homework that's due this week here. So, that was the first question in problem number 3. Is it Markov? And the answer is yes. There are more problems in problem number 3. There are also questions about. So the next part in problem number 3 is it a martingale? This was question number 2 in problem 3. Is Sn a martingale? Is it a sub? Is it a sub martingale? So that's when you have inequalities in one way. Is it a super? We have not talked so much about sub and super martingales in this class. I'm not sure we went over the inequalities, but let me just answer this one here first. Well, so for it to be a martingale, we would have to have the expectation of Sn plus 1 given the coin flips, that this would be Sn, right? Do we have something like that? That's the question. And not really, right? So what we have that the expectation when you discount, we have that this is true. As it is a difference, and of course you can move this 1 plus r. This is a coefficient that is a constant coefficient, and it can be pulled outside. You can write this here as 1 over 1 plus r times the expectation of Sn plus 1 given the first coin flips. And we're given in the problem that r is strictly positive. Right, so this one here is not true. So that's not true. Because r is strictly positive, we know that when I divide by 1 plus r, I'm going to get something that is less. So then there's the question of the sub and the super. This is just to figure out like what kind of inequalities do we then have? Well, if I replace it here with an inequality, can I get any of them to work? Well, let's have a look. 1 plus r, this is going to be less than 1.
Hi, Professor. Quick question.
Yeah.
Where did the 1 plus r come from if it's e to the Sn plus 1? Or if it's like Sn plus 1 divided by 1 plus r?
This one here?
Yeah.
But that's what we mean with the conditional. So remember in the very first one,
I'm just confused because if it was NFSN plus one, wouldn't it be SN over one plus R?
can you say that one more time?
I was just confused because it wouldn't it be SN over one plus R? Wouldn't that be an equivalent for SN plus one?
Right. So it's this property here that I'm using. I'm using that. The property I'm using here is that Sn divided by 1 plus R to the nth, which is Sn divided by Sn0. This is a P tilde martingale.
Okay.
Right. So what does that mean? But it means that Sn plus 1 divided by 1 plus R to the n plus 1 conditioned on these coin flips that this is equal to Sn divided by 1 plus R to the nth. But that's what.
Okay, I see.
Right. So now what we do is we move. This is again a constant coefficient. This is a constant, right? So you can go outside, and so you can cancel out here.
Yeah.
Same thing as saying that 1 over 1 plus R times this conditional expectation, and of course I'm running out of space here. So I want all these guys, right? That this is equal to Sn.
Okay, yeah, I get it.
Right, and that's the
Thank
one. Yep. Yeah. So whenever you have questions like this, now is just it is a really good time to get this squared away, so we don't have to like have discussions about this on Monday and Tuesday. So whenever you have questions like this, just let's get them squared away once and for all, so we're not confused about that. Awesome. We have, so that's the property we have that came from this corner down here. R is assumed to be positive in this problem. So if I take 1 plus R and I divide by 1 plus R, I'm going to get something that is less than 1. So if I take 1 plus R up here, how does 1 divided by 1 plus R times this conditional expectation of, I mean, you can see why at some point we're going to start writing this here as Fn, right? It is just much simpler to write Fn here. So if I do this one, this is small, right? So this here is going to be smaller than, this one here is going to be small. This is positive, so multiply onto a smaller number. I'm going to get that the left-hand side is bigger, right? And this one here was what we knew was Sn. But Sn is small. So when we have this inequality here, this is when you have that Sn is expected to grow, right? We expect Sn plus 1 to be bigger than Sn. This is what we call a sub-martingale property. And this comes from R up here being positive. Okay. Then the third part, this was number 2. The third part is now you're given a different process. You're given this, what is it? S0 times 1 plus R to the nth minus Sn plus. This is a stochastic process indexed by n. And we want to know, is this a martingale, sub, or super? So we want to know about martingale properties. And so whenever you see something like this, the thing that should come to mind is there is a plus here. This is a convex function. whenever you see something that has to do with convexity, lots of payoffs that we're interested in, you're convex, like the puts and the calls. So this is not quite a put, it's not quite a call. Right, you have, if this were to be a put, right, the strike here would have to be not independent, but here it is. But it looks a little bit like a put. It has this positive part in there. Right, so you've seen the positive part, something about martingales. The thing that should come to mind is Jensen's inequality. And Jensen's inequality, just always test it out with this thing that you know, right? So you have x squared, you know the function, the square function is convex, and you know there's going to be a relationship between having the expectation of the function on the inside and then moving the function to the outside. And it's always a good idea to test it out with the square function, because you know what the relationship is. It has to be like this, because the variance is equal to this one minus that one, and variance is the always positive. So when you're in doubt about Jensen's inequality, test it out with the square function. You know it has to be like this, and so from there you're going to get that if I want to compute f of a function given something, I don't know, let's call it g. If I pull it outside, I'm going to have that whenever f is convex. Right, that's Jensen's inequality for conditional expectations. And that's the one we're going to be using up here. So let's give it a shot and see what we get out of Jensen's inequality. So we're going to take the process, evaluate it at time n+1, compute the conditional expectation, and see how it relates to the value that this process has at time n. Okay, so let's get to it. So we'll take the process, we'll evaluate it, we'll evaluate the process at time n+1, and then we'll condition on the first n coin flips. Let me write this now as Fn. Right, so Fn is what we have here. It's just a lot shorter to write Fn. And so we have the convex function. I want to move the convex function outside. So I'm going to use Jensen's inequality. This is Jensen. That's Jensen's inequality. We're going to move this thing outside, keep the rest the same. So inside we'll have S0, 1 plus R n plus 1 minus Sn plus 1, given Fn. And now we'll move the plus to the outside. We get an inequality. So whatever you do with these inequalities, you cannot have, it is a really bad idea to write equality here. When you have a function on the inside of an expectation, you cannot just move the function outside. This only works when f is linear or affine. When it has these convexity properties like this plus here, you cannot just move the f outside and keep the equality sign. Please don't do that on Monday and Tuesday. That's a bad idea. Okay, so now what we're left with here is, with the first thing, there's no randomness. The first thing that has no randomness, this is S0 times 1 plus R to the n plus 1. And then the other one has a minus sign. It has a minus sign, so I have minus E tilde of Sn plus 1 given Fn. And that was the one we had it over here. Like we have that here, this conditional expectation is equal to Sn times 1 plus R. Like that's the one I'm having, so I need to move 1 plus R to the other side. I'm going to get Sn, I'm going to get here that this is Sn times 1 plus R. And of course, there's a plus outside. That plus here carries on. Okay, so I have 1 plus r. I can put that outside. Then I'll have what's inside here will now be S0 times 1 plus r to the nth. Right, I move that 1 plus r outside, and I'll have a minus Sn here. Positive r. And what we were interested in was relating this quantity, like the conditional expectation of the process at time n plus 1. We wanted to relate it to the value that the process would have at time n. And the only difference is this one here. Right, so r is positive, so if I throw it away, I'm going to get an inequality. I'm going to get an inequality. This is S0 times 1 plus r to the nth minus Sn positive r. Right, so we have the conditional expectation. There is a relationship. There is a relationship, and this one here is bigger than its current value. So this is again, it's again a sub-martingale. Any questions on this? Are we all hanging in here? Could we follow these calculations? Yeah, any questions on this piece? So remember, yes, is an inequality. When you have a function that has convexity in it, so a square function, exponential function, the plus function, all these functions here are convex. When you have a convex function, then there's a way to relate the expectation when the convex function is on the inside with what happens when you move the convex function to the outside. Okay? And there's an inequality that you get. So you have to have an inequality as you move along in these calculations. And it just turns out in this particular case that inequality is what's called a sub-martingale. Martingale is going to be when you have equality. Sub-martingale is when the conditional expectation is bigger. A super-martingale is when the conditional expectation is smaller. All right, if there are no questions, then we'll move on to the next one. This one here was number 4. Number five is quite similar to stuff that you have done in one of your homework problems. I think we've done a few of them in class, but let's just do another one. Yeah, let's just do another one. So problem number 5. So you're given here that x is independent of y, and you're given that the standard normal, mean 0 and variance 1. And then you're given a function. You're given a function, it's a square function. So you're given that you want to compute that one, given one of them, so sigma y. What is this equal to? Well, it's going to be a function of y, but what function is it? So that's the question. You're given 2 independent standard normal random variables. You're being asked to compute the conditional expectation of the sum squared given y. So how would we go about doing it? Well, we'll write it, but it's already broken up that you can see that one of them is measurable and the other one is independent. So this one here screams the independence lemma. Like, and as usual, there are two components. We need to know that y is sigma y measurable, but that's clear, right? And then you're going to need that x is independent of y, but that was given. So then what you do is you take out what's measurable. What you do is you take out what is measurable. So this is my y here, so let me write that with a little y. And then you take average over the rest. And then when you're done computing, you replace the dummy with the random variable y. So then you need to know how to compute an expectation, an unconditional expectation. Here you have a normal. So what is that going to be? Well, you can factor this out. This is x squared plus 2x y plus y squared. Okay, and when you're done, you put y equal to capital Y. So you said the expectation is linear, so the expectation of x squared, this is going to give you the variance, right? Because the mean is 0. So this is going to be a 1. And then here you're going to get the expectation of x times 2y, well, the expectation of x was 0. And then you're going to get y squared. And the expectation of a constant is just a constant. And when you're done computing, you replace y with capital Y. So you end up here with 1 plus y squared. So this conditional expectation here is equal to 1 plus y squared. Can we follow this one? Right, so this expectation of x plus y squared given y, this is a function g of y, where g of x is 1 plus x squared. Are there any questions on this calculation? So for the next problems 6, 7, and 8, I have notes that say that we did those in class. Do you want me to go over them again, or do you want me to skip ahead to the later problems? What would you guys prefer?
Later problems.
Later problems, okay. Yeah, so 6, 7, and 8. If we have time towards the end, we can come back and do them. But yeah, so 6, 7, and 8, they were done in lectures. I'm happy to go over them again, but see if we can maybe get through the other problems first and then come back to do these ones. So problem number 9, this one also looks familiar. I'm not sure we did exactly this one in the lectures, but pretty close. So what we're trying to do is in number 9, we're looking at a binomial model, and we always have these properties that d is less than 1 plus r is less than u, and so we have a multi-period binomial model. We have these Bernoullis, UD. You go up with probability p and 1 minus p. And so under this restriction, we can form these risk neutral probabilities p tilde. And personally, I'm having a hard time remembering what the formula for P tilde is, and some of you might just remember it instantly. So the way that I like to do it is that it doesn't hurt just to remember where this P tilde is coming from, right? So it's coming from the fact that the discounted stock price is I want it to be a martingale. So I want Sn plus 1 given 1 plus R divided by 1 plus R. I want this to be Sn. So say that you don't remember what this is. You can always come back to where this formula is coming from, and it's coming from this requirement here. And at this point, we've been over it already a few times today. This is 1 plus R, and it's going to be Sn, right? And then it's going to be P tilde times U plus 1 minus P tilde times D. And so you move 1 plus R to the other side, you cancel out the D's. So the formula is going to come from, right, so I have 1 plus R here, and then on the left-hand side, I'll have P tilde U plus 1 minus P tilde D. And then I can collect terms. I can move this D to the other side, right? So I can put here 1 plus R, or it'll be minus a D, right? And then on the right-hand side, I'll have P tilde U minus D. And then I'll finally get the formula for P tilde, which is 1 plus R minus D divided by U minus D. Right, that's my P tilde. And because of this restriction you have up here, you're going to get the P tilde, and this is a number between 0 and 1. So that's my P tilde. Okay. Then I know what is it? We have a derivative, so we have a payoff. We're going to price a payoff. The payoff looks a bit funny. This is like 1 over square root of Sn. This is the payoff at time capital N, right? So the problem we're facing is similar to the problem we face many times. We have a payoff that comes out here. This is a stochastic, right? This is a random. This is a random payoff. So we cannot just multiply onto the interest rate and move it back. This would never work. But the payoff is coming out here, right? And what we're interested in is figuring out what is the value of it in here at time 0. Like, how do I move it from the future back to where I need it to be? We are interested in the price at time 0. Okay, so the way that we do it, the way that we've talked about it in class, and the way that you guys have been doing it in the homework also for this week, is you roll it back, you compute the conditional expectation, and so you start by going from here, right, to here. You roll it back 1 period to n minus 1, then to n minus 2, and so on, and then ultimately you're going to be back at time 0. So let's try to do that. We go back 1 step at a time. So we discount, compute the conditional expectation of 1 over 1 plus R. We roll it back 1 period, 1 over root Sn, condition on Fn minus 1. Now, Sn is Markov. So I know that this conditional expectation here, this is just going to be a function of the stock price at time n minus 1. I know that this is going to be, I think we call this for Fn minus 1 applied to Sn minus 1 because Sn is Markov. But of course, what is the function? So let's figure out what this function here is. And it goes through the usual recipe, right? It's a constant. We can move him outside, 1 plus R. Then the second step is we need a connection between S capital N and F capital N minus 1. So inside here, this is where I find all the coin flips up to time n minus 1. I need to link this random variable here with these random variables that I'm conditioning on. And the way to go about that is to use the definition of S capital N in the binomial model. And in the binomial model, this is S capital N minus 1 times that coin flip psi n. Given, I can write out the coin flips. So now we're in shape, we're in good shape. We can either use the independence lemma, but in this particular case, the square root has this nice product structure, so we can, if we so desire, right, we don't have to use the independence lemma here because the function has a special property that allows us to break it up more easily. So we'll have 1 over square root Sn minus 1. And then all that's left here is 1 over square root of psi n. That's independent. And I'll be left here with just the unconditional expectation of 1 over square root. I can write it. 1 over square root of psi n. Right, so again, I'm using here I'm using two properties. The first one is that Sn minus 1 is measurable with respect to these guys. That's the first property. And the second one I'm using is that psi n is independent of the previous coin flips. So this is quite similar to what we've seen a few times before. I'll have here 1 over 1 plus r, and then I'll have 1 over Sn minus 1, and then I need to compute this expectation. So this will be p tilde. This is when psi is a u, so this is 1 divided by square root of u. Don't put this 1 over square root together with the p tilde, doesn't work like that. And then there's 1 over square root of d. Yes, so we have that. This is my function of fn minus 1, because you can see the only random component that's left here, and I'm missing that square root, is the square root of Sn minus 1 down here. Any questions on slides, on these slides here? It looks good. So that took us from time n to time n minus 1. So let's try to go to time n minus 2. So I'll need to take this object here and condition one more time. So the next step is to compute the conditional expectation of 1 over root Sn given, but now I only know the coin flips up to the second to last time step. Okay, so I'll do that, plug in what I have here. This is 1 divided by 1 plus r times p tilde, 1 over root u plus 1 minus p tilde, 1 over root d, and then the conditional expectation 1 over root Sn minus 1, condition on this fn minus 2. Okay, so what do I get this time? Well, if I start working out what this here is, I'm gonna get maybe I should have been a little bit more careful here, right? So this is true. Maybe I should have been a bit more careful here. I should have taken this payoff here and discounted it. So should have been a bit more careful here. Should have been a bit more careful here. This should have been I should have discounted it out 2 places. So this is 1 plus r squared. Yeah, 1 plus r squared. I'm going from n to n minus 2, so I need a square there. And I need some more space here. Write it out 2 steps so we don't create any confusion. Right, so this here will be equal to, well, it'll be 1 over 1 plus r conditional expectation, and then the thing that I just computed, conditional expectation of 1 over 1 plus r, 1 divided by square root Sn, and then I'll condition here on Fn minus 1, and then I'll condition on Fn minus 2. And this here was what I had computed. This is what we had already computed. That was that formula up here. 1 over 1 plus r, 1 over root Sn minus 1, p tilde, 1 over root u plus 1 minus p tilde, 1 over root d. So I can combine the two, but you can see now what I end up needing to compute is, what I end up needing to compute is very similar to what I had before. I can put all the constant coefficients outside the expectation. So this will be 1 over 1 plus r squared, p tilde, 1 over root u plus 1 minus p tilde, 1 over root d, and then the conditional expectation of 1 over root Sn minus 1 given Fn minus 2. Right, and this was exactly this is the same structure as what we had here. So we go through exactly the same calculations one more time, and you'll end up with this formula here again. So it repeats itself. And what I'll get is I'll get another one of these factors. I'll get another one of these factors. This would be 1 over 1 plus r squared. And I'll get one more of these factors. This will be p tilde, 1 over root u plus 1 minus p tilde, 1 over root d, and now squared, and then 1 over square root of Sn minus 2. And then you can keep going. And in the end, you'll have 1 over 1 plus r to the nth of 1 over root Sn. What would it be? You keep iterating this thing here backwards. Keep iterating this thing here backwards. It'll be 1 over 1 plus r to the nth, and then it'll be this factor here to the power n. One over root d to the power n, and then I need 1 over the square root, the square root of S0. So this is the price. That's the quantity. That's the quantity out here in the at time 0. Any questions on this calculation we had? Problem number, which one was it? Number 9? All right, if that's not the case, then I suggest we take a little break, 10-minute break, and then switch over to the other Zoom link, and then we'll try to solve the rest of the problems. And there's also there was a question about the credit default swap, so we can do that one at the end too. All right, I'll see you in a few minutes.